Hi everyone, today we want to talk to you about the conceptual architecture analysis of flight gear. We are the group 6 and here's our group link. Here are our group members. Firstly, let me introduce the introduction and overview for you. In our study, we focused on a comprehensive analysis of flight gear's conceptual architecture. We described the evolution of its software across versions in detail and the importance of concurrency in improving performance and user experience. This research examines multi-threading, task management, and network collaboration in the simulator. It focusing on the implementation of an open-sync graph for graphics processing and a high-level architecture of multiplayer operations. It also addresses control and data flow within the system to ensure a cohesive and immersive experience for all users in a multiplayer gaming environment. Actually, at first, we didn't know what 5G exactly was, so we went to download that and try to play it. During our gaming time, we discovered that flight simulators involve complex physics and environment simulation. This computation-intensive task can be handled by powerful servers, while clients are responsible for rendering graphics and processing user inputs, effectively utilizing resources and distributing computational load. The software also supports multi-user online interactions, and the client-server architecture effectively synchronizes state across different clients to ensure a consistent simulation environment for all users. The server enables real-time updating and maintenance of simulation data, such as weather changes, season changes, and different geographical information. After that, we generally agree that the architecture style of flight gear, at least one, is client-server architecture. Then, because the software contains a large amount of weather and aircraft mode data, we thought that this perhaps was also a reciprocity architecture, but soon realized that it was not, because it is designed as a flight simulator and not for managing inventory or repository operations. This means that although we can change information within the application, it focuses on simulating the experience of flying the aircraft, including the physics of flight. Thus, changing the weather and flight model gives you the ability to define settings, but not change data. Last, we conclude that the important architecture of a flight gear is object-oriented architecture, because the implementation of a flight simulators primarily focuses on object-oriented programming. As we discussed before, flight gear simulates real-world flight conditions and requires a high degree of physical accuracy, graphics rendering, and user interaction. Anyway, we could make sure that the two main architectures of flight gear are client-server and object-oriented. Also, we announced what software architecture is used in the subsystem. We can see that both the visual system and the sound system use the client-server architecture. It's in order to allow multiple components to manipulate the data and process application by recording the actual aircraft sound and announcing the source to simulate the sound waveform. The motion system and the navigation system adopt a layered architecture style. These layers include a computational accelerated flight model, we also call the logical layer, and also a data layer, a security layer, and so on. Also, multiple navigation technologies are integrated to provide different navigation requirements. So, do you think any limitations in any of the software architecture I mentioned?
For the limitation, as the number of clients increase, the client-server style may introduce the bottleneck that lead to the performance degradation. In addition, network lag can affect the real-time and stability of data transmission. When network latency or package loss occurs, the clients may experience delay updates or lose synchronized with the server, affecting user experience and application performance. Let's begin to talk about the concurrency and the control and the data flow. The concurrency is a critical concept in software architecture. At the core, it allows for the processing of multiple tasks at once, such as handling user input from various devices like keyboard and enhance real-time response to stimulate the actual flight condition. With multi-threading, a key technique in concurrency, flight simulator can execute different tasks on thread. For instance, where one thread handles the dynamic of the aircraft, another might manage rendering the graphic. The division of labor allows the smoother, more responsive stimulation, minimize the chance of performance bottleneck that could arise from the single-threaded process. The OpenSync graph library used the multi-threading to improve the performance of the graphic remembering. A significant aspect of flight simulation, it allowed for the parallel processing of multiple remembering tasks, optimize CPU usage, and reduce the total remembering time, which is important for maintaining high frame rate and seamless user experience. Moreover, concurrency enable network operation and multi-user operation in flight simulators through the high-level architecture framework. Different simulator systems can work concurrently in a shared environment, synchronize data in real time, and allow for interactive multi-user scenario. HLA supports the independent operation of each simulation component while still enabling real-time communication and interaction among multiple users. In summary, concurrency in flight simulator is about efficient multitasking and resources management, ensuring a realistic and immersive user experience by allowing multi-use processing to execute and interact properly. This graph shows the interaction between the user and the flight simulator system. User may have function to choose from, such as starting the simulator, select the aircraft from the local dictionary, and control the aircraft during flight. Option for setting environmental condition and pausing, changing the graphic setting, or resuming the game are also present for the user. In addition, the user can interact with the feature that the autopilot and receive feedback through the graphic and sound output. Multiplayer functionality is implemented through servers, which allow users to connect with others. AI generates traffic control system and engine behaviors from part of the simulation dynamic environment. Now let's begin to talk about two use cases. The first use case is about the pilot gameplay. This use case shows how flight gear work when players control the aircraft. The user first decides to start flight gear and select either single player or multiplayer mode. If the player chooses to play in multiplayer mode, a server connection occurs. Before running into the game, the user has the option to set the environmental condition like the time, weather, visible, even using the live world weather. Once the user starts logged into the game, the autopilot system may be engaged. The user input command uses the I/O device like the keyboard to control the flight. These commands are transferred through the flight controller to a simulation system and provide feedback on state of the aircraft. The graphic engine calculates and displays the flight and the environment to the user. Also, the sound engine plays audio effects such as the engine noise to make the simulator more realistic. The AI component in flight gear work as the air traffic control and may generate content-specific behavior or events. Now let's begin our second cases, the multiplayer gameplay. The use case show how flight gear work in multiple player mode and how player communicate. The graph show how flight gear system manage interaction during the multiplayer mode. Both the ATC player and the pilot interact with the system use gear. The pilot and the ATC players connect to the service through the grid. Once connected, the pilot has control capacity which are uploaded to the server. The server gives the command and input to the main process, where the main process contains all engines and control you in the use case 1. After that, the movement and information is transferred to the database. Both sound input and sound effect are processed separately. Input sound process are uploaded to the database and reflect back to the communication system so that the APC players are able to receive and read the direction of aircraft within the radio range through the rail. The communication system is like handling real-time interaction and feedback within the simulation. Throughout this, the continuous loop ensures the display is updated and the pilot and ATC player receive immediately feedback on the action. Overall, the control flow represents the live execution of the simulation. React to both pilot input and system event for the immersive flight experience. In contrast, the data flow involves the management of simulation data, including the connection and achieving together these two strengths create a framework that not only stimulates flight but also supports the multiplayer interaction online. So that's everything for today. Thank you.